Okay, so hello everyone. Thanks for the chair for the introduction. I'm Weiran from Alibaba Group, and today I will present our work. It's a long title, Unbalanced Circuit-Private Set Intersection from Oblivious Key Value Retrieval. This is joint work with Meng from Nanyang Technical University and Liqiang Peng from Alibaba Group and Hongwei Li from the Peng Laboratory and Zhang from Tsinghua University and Hanxiao Chen and Tianwei Zhang also from the Nanyang Technical University. And my presentation consists of 4 parts: introduction to Circuit-PSI, existing Circuit-PSI framework, OKVR and UC-PSI construction, and finally, the implementation and performance. So let's come to the first part, introduction to Circuit-PSI. So let's first come to the PSI. So PSI enables to compute the intersection of private set. The client only learns the intersection while the server learns nothing. And PSI has been extensively studied in the last 2 decades for a balance setting. Some schemes achieve linear complexity and almost as efficient as in-square hash protocol. And for unbalanced setting, some schemes achieve sublinear communication complexity of large set size. And other PSI variant has also been proposed. For example, the two-side PSI allows both parties to learn the output. And the PSI-CA allows the client to learn the size of the intersection. And the intersection sum allows the client to learn the sum of the intersection. And the last PSI variant allows the parties to compute some other functions based on the intersection, such as threshold PSI and payload computation. We can implement the last PSI variant. Also, we can implement the PSI-CA and PSI sum by Circuit-PSI. So Circuit-PSI enables the client to learn the result of a function on the intersection without leaking the intersection itself. So the definition is shown in the above figure. Here, f is a post-processing function, for example, the intersection cardinality or a threshold function. We can construct the Circuit-PSI with 2 steps. The first step is to compute a Boolean share indicating whether an element is in the intersection. The second step is to do general 2-party computation with the help of the Boolean shares. So what we need to first consider is how to implement the first step. So this works on Circuit-PSI in the unbalanced setting. That is, the client processes a set with a smaller set size T, and the server holds a set with a considerably larger set size N. So unbalanced Circuit-PSI also has several applications such as password leakage detection, image abuse detection, and UC-PSI with associated data. Well-famous example is the Apple PSI system that uses PSI with associated data and threshold PSI with associated data. So let's turn to the second part, existing Circuit-PSI framework. Existing Circuit-PSI construction has 4 steps. The step 1, the client inserts its set into a Cocoa hash, and the server inserts its set into a simple hash with the same hashes as the Cocoa hash. In step 2, 2 parties run OPRF to let the server learn the OPRF key K, and the client learns the OPRF output of their set element. And step 3 is OKVS, and step 4 is PQT. So what is OKVS? OKVS is the data structure that encodes a key value map with set N to an array D with set M, where M is greater than or equal to N. OKVS encoding is equivalent to solve a linear system shown in the right figure. Here H is the mapping function, and different OKVS constructions have different definitions of H. OKVS need to satisfy the following 3 properties, namely the correctness. So for any key value maps, if D is in the encoding result, so if D is the encoding result, then for any key Qi, Q equals Ki, the decoding value is the same as the encoding value. And obliviousness means for any 2 key sets, if V is chosen randomly, then 2 encoding results should be indistinguishable. And there's an optional property, binary. So HK outputs a Boolean vector. And this work focuses on the binary OKVS. So a typical OKVS example is a polynomial. That is, the encoding result is a polynomial interpolations of a given key value map. In polynomial OKVS, we can define H as the k to the 0, k to the 1, k to the 2, up to k to the n minus 1 to solve the linear system. So the rate is optimal. That is, requires all Ki and Vi are in the same field, and it is not that efficient to encode and decode. Another OKVS example is a couple-Google table, GCT. This is what we use in our scheme. So we can define H as a Boolean vector indicating positions of D, and decoding is done by XORing the corresponding positions. So due to time limitations, here I ignore the encoding algorithm. But I want to note that there are several works on improving the encoding algorithm for the GCT constructions, and all of them are very elegant, and I recommend taking a look. So the last primitive is a PEQT that enables two parties to privately compute the two values and obtain the shares of whether the two values are equal or not. We can use general two-party computation to implement the equality test functionality. We can also use other solutions such as the batch N or the protocol introduced in the CryptoFlow 2 to do equality tests in a tree-like manner, saving the round complexity. So there's a lot of primitives. Now let's turn back to the Meng construction. So if we plug in suitable sub-protocols into existing Circuit-PSI framework, we can find that we almost achieve our goal. The goal is to making the communication complexity sublinear in the large side. So for example, we can let the client to do the Coco hash so that the number of beans are related to the small set T. And we can also use a DH-based OPRF so that the server can generate the key by itself and evaluate the OPR result of its element without any communications. So the difficulty is in step 3, OKVS. Here in the framework, the server needs to send the whole OKVS encoding result to the client so that the communication is order of n, linear in the large set. So what we do is to define a new primitive named the Oblivious key value retrieval that asks the server and the client to run a protocol instead of directly sending the whole OKVS encoding to let the client retrieve the value from the OKVS owned by the server, and with the communication sublinear in the size of D. So the core of OKVR is sparse OKVS. That is, we can find OKVS that can split the encoding result into a sparse part D0 and a dense part D1. The dense part is of size sublinear in N, and the sparse part has constant weight alpha. So note that the GCT is a sparse OKVS, where the dense part size is order of log N, and alpha equals 2 or 3. So someone would find that OKVS is similar to the keyword PIR. So here are some differences. So OKVR enables client to obviously retrieve values, so a batch of values from the server's key value pair for all key required by the client. On the other hand, keyword PIR enables the client to obviously retrieve a value from a server's key value pairs and know if the server has the key or not. So in short, OKVR is for batch queries, protect server privacy, and client knows a random value if the query is not in the key value pair. So that's the difference. So we can easily use batch PIR to construct OKVR. So step 1 is just a simple OKVRF, and in step 2, we ask the server to directly send the small dense part. So because the small dense part is really, really small, we can directly send that in offline freeze. And in step 3, we ask the client and the server to run batch PIR so that the client can retrieve necessary values from the OKVS and then decode by combining the dense part and the retrieved values. So using OKVR, the server does not need to send the entire OKVS encoding result to the client. Instead, they can run OKVR to implement OKVS decoding with little or n combination cost. So the total combination cost for the whole construction is sublinear in n. So the construction is pretty simple, right? So let me briefly show the implementations and the performance. We provide a unified unbalanced Circuit-PSI implementation, including known unbalanced Circuit-PSI protocols with optimizations like silent OT. So the source code is available at the submodule MPZ4J S2PC UPSO of the open source library MPZ4J. We compare the performance of our constructions with standard Circuit-PSI and concurrently proposed unbalanced Circuit-PSI construction at G23, accepted by the agency says 2023. So here's the performance result when the large set size is n is 2 to the 20. So we can find that when T is relatively small, our construction outperforms existing state-of-the-art solutions. And here's another terrible table, performance results when the large set size is n is 2 to the 22. Similarly, when t is relatively small, our construction outperforms existing state-of-the-art solutions. So that's it. Thanks for listening, and I'm happy to catch and answer any questions, and especially I'm the developers of this open source library. So please let me know if there are some bugs or some problems about the source code. Thank you very much.